we're trying to prove a congruence here with a fairly large modulus. Another way to state this is you can state it as a divisibility problem. We'll use the vertical bar. And what this states, this congruence p to the 8th is congruent to 1 mod 40 is the very same thing as saying is 240 divides p to the 8th minus 1. Now there is a caveat here. This is only good for primes greater than 5. That is 7, what's the next prime? 11, 13, and so on. Okay, so in other words, we're trying to establish this for these primes 7 and greater. Okay, now you'll see why this is true if you just take a look at the prime factorization of 240. Notice 240 decomposes into 2 to the 4th times 3 times 5. That's 16 times 15 is 240. And so you can sort of anticipate that these 3 primes wouldn't be included in this truth right here. Okay. Now let's talk a little bit about something called the Euler Totient function. The Euler Totient function counts the number of relatively prime values to a given number, and in this particular case all the odd numbers are relatively prime to 16. That is 1, 3, 5, 7, 9, 11. Not really necessary to write them down, but we will anyway. These are the only odd numbers less than 16, and that means they're the only numbers that are relatively prime to 16. Again, there's 1, 2, 3, 4, 5, 6, 7, 8, and so that's why this thing called phi of 16 is equal to 8. All right. Now you can almost define a prime number, phi of a prime, since the prime number is only divisible by 1 itself. This is going to be equal to p minus 1. Phi of any prime will be p minus 1. Literally, you can think of it as a definition of a prime number. No, there's no such thing as phi of n equals to n minus 1 would be equivalent to n being prime. Okay. Now, why is that important? Well, there's something called Euler's formula that is an enormous aid in reducing exponential expressions, the exponent in exponential expressions. And it's something that holds provided that the base and the modulus are relatively prime, that is, they share no common factors. Now notice we can rewrite this in a way that's actually quite convenient. We know that phi at p is equal to p minus 1, so you can rewrite this in a form that's very popular. It's called Fermat's, I think, little theorem. But notice phi at p is equal to p minus 1, so for prime n we get this. Mod p. So this is often proved separately, I think, in some number theory textbooks, but it's really an immediate corollary of this, I guess, this broader theorem, which is result. It's called Euler's Phi Function Result, whatever it's called, you know. But anyway, so these two results come in quite handy right here, because let's just go on down. You can see that we applied this version of it for the mod 3 case. Remember, 3 is one of the prime factors, and so this would be 3 minus 1 right here. Right here you would have 3 minus 1 gives you 2, and then for 5 minus 1 is 4. And also we use the fact that we established at the very beginning, or yeah, here it is right here. Phi at 16 is 8, and so what we get is p raised to the 8th is congruent to 1 mod 16. Okay. Again, do I keep it all on the same screen? Yes, there it is. We use this version of it right here for the bottom congruence, right? But notice something very nice happens right here. This is the very same thing as saying that 3 divides p squared minus 1, and this is the same thing as saying that 5 divides p to the 4th minus 1. So that means that if you multiply these congruences together, you can change the modulus to 15th. That is, these two statements right here imply that p to the 8th is congruent to 1 mod 15. And again, that's just basic divisibility. It's nothing too sophisticated. Okay, folks, again, p squared minus 1 is divisible by 3. P to the 4th minus 1 is divisible by 5. And so that forces p to the 8th minus 1 to be divisible by 15, right? I mean, that's just basic divisibility, right? Okay, but notice if you combine this one with this one, we get what we're looking for. In other words, p to the 8th minus 1 is divisible by 15 and 16. And so that means that p to the 8th is congruent to 1. And I'll write this down just for emphasis. If you think about divisibility, you don't worry too much about the rules here. You know, it's a very sensible way to think about it just in terms of divisibility. So I'll write down 16 times 15. Okay? And really, we're just using this idea that we used here twice. You see, we used the same idea for these two statements to imply this statement, and now we're using this statement combined with this statement in the same fashion, okay? So anyway, of course, that's equal to 280, and that's what we're trying to prove. Or wait, 240, excuse me. 16 times 15 is 240, right? So we're at a QED time. Okay, done. Now, I want to just make sure that's what we were trying to prove. Yes, it is. Okay. Now, y'all, just a little bit of insight on what you just done right here. If you pick some prime, I'll just make up a prime. Let's do p is equal to 29. That's a prime number, right? What this really means is that 29 raised to the 8th power minus 1 divided by 240 has a 0 fractional part. Another way of writing this is that this is some natural number. I'll call it n. I don't even know how to make the right kind of n. There's some kind of Roman way to make. Does it look like this, maybe? Something like that? Okay. Yeah, but these are the natural numbers here. And so that's exactly what this statement says. Elevate 29 to the 8th power, subtract 1 from it, and you'll get a number that's divisible by 240. So in any event, there's nothing special about 29, any other prime, other than, and I hope you guys see why we couldn't use 2, 3, and 5. It's because we need for the base and the modulus to be relatively prime for these results to hold. And also, I'll just go ahead and mention as a side, this is often called Fermat's little theorem right here. Okay, but anyway, we're done, and I hope you enjoyed it.